welcome to Numerical Ship and Offshore Hydrodynamics. Today, we are going to discuss about the incident wave and wave force, okay. And this is the keywords to get this lecture. Before we start, let us see the visualization of the wave elevation. Okay. Now, you can see that water particle actually moving in this circular fashion, and then that this wave is propagating in the horizontal direction as follows. Now, this green dot basically tells you about the wave amplitude, and then then when it make the complete circle, that means green dot comes down and up, it actually travels from this peak to the next peak, right. You can see that. Now, with this visualization, let us move forward. Now, here I can, as I said, that when this green dot makes the complex rotation, like it go down and then come up, then this waves moves this peak to the next peak. Okay. Now, this we call the wavelength, that means the length of the wave when this water particle complete one circulation or one rotation. Secondly, we call from this 2 to minus 2, that complete that height from the top to the bottom, we call this is the height of the wave. Okay. And this top part we call the wave crest, and this part we call the wave trough. Now, from the classical that angular motion, you know that this, if omega is the frequency and t be the time period, so both are the having a relationship with omega equal to 2 pi by t, right. Okay. So, that means that water particle takes the time capital T to get the complete rotation. Now, similarly, as I said that for a full rotation, these also travel the lambda length. So, then we can define one parameter k, which is called the wave number. It means that similar to the wave the wave frequency omega. So, meaning is same, one is in the respect to the time and one is the respect to the space. Now, how to understand this? Basically, that if you take this snapshot here, so we can have a harmonic, that means you are fixing your at any point of time, suppose you can see some progressive wave, and then at each point of time you take a snapshot, you can find that this sinusoidal pattern. Now, similarly, what we could do is that if you fix a point x, let us say you fix a point over x like this green dot, and if you see the oscillation of the green, then you can see a harmonic motion. So, this is harmonic in the direction of x if you take a snapshot, if it is harmonic in the direction of the t also. So, in case of a direction of t, we have the frequency omega, in direction of a x, that means direction of the wave propagation, we call this since this is all harmonic. So, we call this as a wave number. So, here it is omega equal to 2 pi by t, here is k equal to 2 pi by lambda. Okay. Now, as I said, if you fix take a snapshot, if you take a snapshot, then this signal is eta x equal to a cos k x. Now, if you fix the space and if you just look at the motion of this green dot, then eta is basically, you can see it is a cos omega t. Now, you see here this eta is a function of both. If you take a snapshot, you can find a sinusoidal curve, which is this one, right. And also, if you only follow the motion of this the green dot, which is comes ups and down. So, if you try to plot that, then again you can get a sinusoidal curve, right. So, therefore, eta is actually function of both function of space and as well as function of t. Now, let us try to understand some more definition, which is called the speed of the wave. Now, here you can see that this t basically the time period, it says that as this water particle, which is the blue dot, moves a complete circle, if I take a time t, at that particular time t, these waves move horizontally the lambda distance. So, therefore, the wave speed should be lambda by t. It means that if the particle, water particle takes a complete circle in time t second, then this wave travelled along the x direction is lambda meter. So, therefore, we can define the wave speed c equal to lambda by t. Okay. So, now let us try to understand that what would be the equation of the wave in that case. We understand that it is function of x, it is function of t, then what would be the combined equation, that means a wave which is propagating in the positive x direction. Now, before that we need to understand some concept of the phase. So, let us see the video. So, we have the same wave, however, the frequency is same, but it has some phase. Now, if you look at this carefully, you can see that as if this wave profile is actually slowly moving forward, right. This is something we can call as a progressive wave. Just see carefully, this slowly it is moving forward. So, now you can see what I am trying to do here, that I am making the phase from 2 pi into 0.8 to 0, and I can see that what is actually happening. Now, let us see this video fully and then we can understand. Now, you can see here earlier there will be a bunch of waves are travelling, and now only a single monochromatic wave is travelling. So, what is happening? Now, let us see again this video one by one. Now, here what I can see is there is all the waves have some phases and moving. Now, as if you can see that this wave is basically the propagating in the forward direction. Let us see again, it appears you like this wave is propagating, a wave is propagating in this fashion, right, from the left to right, right. Now, what I am making slowly I make all the phases equals to 0. So, that means I am initially is 0.8, then 0.6, then 0.4, then 0.2, and then finally I can get the phase equal to 0. So, once I do that, I can see that this see now slowly this wave is not propagating. You see, like if I make this video a little bit here, maybe here. Now, you can see that wave is like propagating slowly. Now, you see that as we are making phases equal to 0, I can see that wave is not propagating as such, it is like only a single motion. Now, you can see when the phase equal to 0, it acts like a monochromatic, a single wave. So, it is you do not have this visual impression that wave is propagating. So, this visual that thing will only coming when I can see lot of phases are there. So, if I make everything 0, then it is as if there is a one single wave is moving. Now, this let us try to understand what is this. Now, this is the first thing you can see, let us say that assume that wave is moving slowly from here to here. Now, this phase let us see the in some other way, like in this phase, if I assume that basically wave is travelling with a speed c, right. So, what is happening in this particular picture, Now, I can assume that this along with this the dotted black wave, this dotted black wave basically it is travelling progressively from green to T. Okay. So, again I can consider, let us see that all these waves has the different speed, let us say. Okay. So, therefore, I can assume that if one wave is cos x, another wave may be cos x plus and then delta c t, that you can think of a phase. Okay. So, idea is very simple. Now, here from here to here, this let us say the wave travelling in progressive ways travelling forward, it will, if I take the time t. So, therefore, this distance definitely c into t. So, that means after time t the wave travel x, I mean the wave travel c into t distance. Now, if I make x minus c t, if I make x minus c t, basically what I do, I cannot see this wave is progressing either, that is from the visual the MATLAB that you can see from here, I can see it is actually a monochromatic wave, and this wave basically can have a unique definition, right. So, here the point is, if we assume this x minus c t, then actually visually I can see there is only single wave, and this equation of these waves can be written in forms of eta equal to a cos k x. So, this is the idea, this is the idea that I am assuming that the velocity, if the velocity of the wave is c, so at t time it is moving x minus c t, since that is how it is progressing. Now, if I take capital X equal to x minus c t, then actually I am getting a simple wave which is travelling along x and with a frequency k, and then equation for this particular wave is eta equal to a cos k x, right. Now, if we understand this visually, then remaining part are simple algebra, we really do not have to think much. Now, if I understand this, really this physics part what I am trying to say, that x minus c t is as if a monochromatic wave with the frequency k, then the signal should be a cos k x. Okay. Now, what is happening here, I can write then eta equal to a cos k into capital X. Now, this capital X is nothing but x minus c t. So, therefore, I get a equal to cos of k x minus k into c into t, right. Now, I replace the value of k here. So, k equal to 2 pi by lambda, and you know the c equal to lambda by t. So, if I replace over here, so I will get a equal to cos of k x minus 2 pi by lambda, then lambda by t into small t. So, lambda lambda cancelled out. So, I will get a cos k x minus 2 pi by t into t. Now, I know that omega equal to 2 pi by t. So, therefore, finally, I can find out my eta equal to a cos k x minus omega t. Okay. So, this is my final equation of the linear progressive wave. Okay. Fine. So, now let us go back to here and try to solve the boundary value problem. Okay. So, let us try to solve this boundary value problem. Now, our governing equation is del square phi r t equal to 0, and these are the boundary conditions. Now, we have this free surface boundary condition phi t t plus g phi z equal to 0. We have the body boundary condition phi n equal to V n, and we have the bottom boundary condition phi n equal to 0, and then we have the initial condition and the radiation condition. Now, here since the problem is without the body, right. So, we can discard this boundary condition, because we do not have the body here, right. And also let us do one thing, this combined free surface boundary condition, let us split into a kinematic free surface boundary condition, which is phi z equal to n t eta t, and then the dynamic free surface boundary condition, which is phi t plus g eta equal to 0. Okay. So, this is my boundary value problem. I am going to solve del square phi equal to 0 with phi z equal to eta t, phi t plus g t equal to 0, phi n equal to, I mean this of course at z equal to 0, and then the normal velocity phi n equal to 0 at z equal to minus h, and then we have the initial condition as well as the radiation condition. Okay. So, now we are assuming the plane progressive wave eta equal to a cos k x minus omega t, where eta is I mean where a is nothing but the wave amplitude, k is called the wave number, omega is a frequency, right. Now, to solve this I am assuming the trial solution phi equal to f z into sin k x minus omega t. Now, the question is why I select this as a trial solution? Answer is very simple. Actually, I know that it is harmonic in x direction, right. The wave is harmonic in x direction, not in direction of the z. So, therefore, the phi must be harmonic in the x direction. So, either this should be the sin k x minus omega t or cos k x minus omega t. Then why I select it is sin k x minus omega t, right. Now, this is the answer also very simple here. Now, you have, let us find out, just guess that my kinematic body boundary condition, which is nothing but del phi del z equal to del eta del t. Now, if I differentiate eta with respect to t, I will get here is sine function, and if I differentiate phi with respect to z, again I am getting the sine function. So, therefore, looking at this, I know that if my eta equal to a cos k x minus omega t, definitely my solution become f z into sin k x minus omega t. Okay. So, with this understanding, let us go forward. Now, I am taking the Laplace equation phi x s plus phi z z equal to 0. So, there is many ways of writing the same thing. I can write del square phi by del x s square, or I can write phi x s or phi z z, both are the same thing. So, now if I substitute this phi here, so what I get? If I differentiate phi with respect to x 2 time, then this minus k square will coming out. So, I have here minus k square, and then if I differentiate phi with respect to z, then we have this function f z, so it should be the f double dot z, right, fine. And then I know that since sin k x minus omega t cannot be 0 throughout, so definitely the other part should be 0, and therefore, I can get a very simple differential equation f double dot z minus k square f z equal to 0. Now, also we know what is the solution for this particular problem. I know that there is the solution technique that you can take z equal to the power f equal to the power k z, and you can substitute over here, and then we can find out the solution is very simple, f z equal to c 1 e to the power k z plus c 2 e to the power minus k z, right. So, this is very elementary till this point. I mean the solution itself is very simple, but you understand that how to get this solution for f z. Now, in the next what I am going to do is I replace this f z, this value c 1 e to the power k z plus c 2 e to the power minus k z into the solution of phi. Okay. So, now my trial solutions become c 1 e to the power k z plus C 2 into e to the power minus k z multiplied by sin k x. Now, here I am going to apply the bottom boundary condition, which is del phi del z equal to 0 at z equal to minus h, right. Now, of course, you know that at the bottom that normal del phi del n should be del phi del z, right, because you know that in bottom is horizontal. So, normal is the z direction. So, it should be del phi del z. So, if I apply this, what I get? So, if I differentiate with respect to z, if I differentiate phi with respect to z, so definitely k will coming out, right, and also I put z equal to minus h. So, it should be the k z should be minus k h, and then minus k z should be k h, right, and if I differentiate the second term, the minus should be coming out. So, definitely I am going to get this. So, from here what I get? I can get C 1 e to the power minus k h equal to C 2 e to the power k h, right. The both the value is same, and let us take that both the value is same and it is same as C by 2, where C is itself unknown to me. I can do that, right. There are many ways to do that. I can replace C 1 equal to C 2 e to the power k h plus, I mean 2 k h, that also I can do, and I can proceed further, but there is a different way of solving the same thing. So, this is the way that we are going to solve. So, I am taking C 1 e to the power minus k h equal to C 2 e to the power k h, and both is equal to some C by 2, and from here I can get the value of C 1 and C 2. So, I get the C 1 equal to C by 2 e to the power k h, and I am getting C 2 equal to C by 2 e to the power minus k h, right. So, now I know the value of C 1, I know the value of C 2. So, definitely I am going to substitute over here, right. So, once I substitute and I do some mathematical adjustment, I will get the first term C into e to the power k z plus h, I get minus k into z plus h by 2. Now, this is a hyperbolic function, right, it is cos hyperbolic. So, therefore, I can get the solution phi equal to C cos hyperbolic k z plus h into sin k x minus omega t, right. Now, here still I do not know the value of C. So, I need to find out the value for C. So, we need to use some more boundary conditions to get the value for C. So, in next I am use the dynamic free surface boundary condition to get the value of C. Now, you see this is my eta is a cos k x minus omega t, and then we have the phi, which is my velocity potential, or you can say it is incident wave potential, that we say it is C into cos hyperbolic k z plus h into sin k x minus omega t, and then I differentiate phi with respect to t, and then I substitute the value for eta and I put z equal to 0. So, once I do that, I can find out this expression, right. So, this of course, this if you differentiate with respect to t, that this minus omega will coming out, right, and then you put z equal to 0. So, here you can put the z equal to 0. So, I cancel this. So, I put z equal to 0 over here, and then I can solve for, and also here I can make an argument that cos k x minus omega t cannot be 0, of course, and then we can obtain the value for C, which is a g divided by omega cos hyperbolic k h. Now, this value of C I need to substitute over here in phi, and once we do that, I get the expression for the incident wave potential phi I equal to a g by omega cos hyperbolic k z plus h sin k x minus omega t divided by cos hyperbolic k h. Now, this is for the finite depth, right. So, you see like we have the another boundary condition. So, if I apply this another boundary condition, what we get? Now, if I apply this kinematic free surface boundary condition, and you can work out, that means phi z equal to eta t at z equal to 0, if we use it, then you will get a relation between the omega and k, which is called the dispersion relation, right. So, this is of course very important relation for us, I mean and this is very important because this tells you very nice phenomena about the waves, the difference between the water wave, to sound wave or electromagnetic wave, but at this in this course we really not going to discuss the physics part of it, rather we are much more interested to the solving this problem. And so, therefore, we are going with the deep water situation when actually you can take h tending to infinity, then tan hyperbolic h equal to 1. So, then the dispersion relation for deep water equal to omega square g can, we are going to use this results in future, because in ship hydrodynamics we are mostly dealing with the condition where you can assume that the water depth is infinity. I mean so, therefore, we are going to take this dispersion relation. However, the physics part of it is definitely very important, and separately one can discuss in other courses, but here we are focusing only on the numerical part of it. And also the dispersion relation for the shallow water is c square equal to g h, that also very elementary, take h tending to 0, then tan hyperbolic k h equal to k h, and if you solve this you can get the c square equal to g h this thing, but we are not going to use this second thing, we are definitely going to use the omega square equal to g k. So, now this is to the velocity potential we are going to use. Mostly I am not going to use this phi 1 in the finite depth, rather we assume our all ship structure interaction, I mean ship wave interaction is on the deep water. So, therefore, we are going to use the incident wave potential phi I equal to a g by omega e to the power k z into sin k x minus omega t. Okay. Now, let us see that how I can find out the various physical parameter from this velocity potential phi I equal to a g by omega e to the power k z sin k x minus omega t from here. Now, here this eta equal to a cos k x minus omega t, and then I can get the velocity in horizontal direction, it is del phi del x, and so this is the expression for del phi del x. So, I can get the horizontal velocity, I can get the w also, that means the velocity along the z axis, and also I can get the, most importantly I can get the dynamic pressure also using this relation p equal to minus rho del phi del t, and which is the expression is a g rho e to the power k z cos k x minus omega t. Now, this is extremely important for this course. This is how I can get the pressure around the body, right. What is the pressure because of this incident wave potential around the body, and this is the expression. Now, once I integrate this pressure, I can get the force, and that force is called the Froude-Krylov force, and this is the one of the major force for my the ship wave interaction. Okay. So, we understand that now I have the expression for phi I, and I can get I can get the pressure over the body so easily, because it is an analytical expression, and if I integrate this pressure I can get a force which is basically the Froude-Krylov force. Now, again let us go back to my so here some visualization that to tells you about the fact that everything cannot be peak at the same time. Okay. So, let us see here, you can see that u velocity, w velocity, acceleration and acceleration at w direction, all is not getting peak at the same time, it is a phase. So, this tells you that importance of the phase, not necessarily that force is always all the forces is peak at the same time, because sometimes that u velocity when the maximum, then w velocity is not maximum. When the acceleration in the horizontal direction is maximum, that time acceleration in the vertical direction also not maximum. So, this visualization helps you to understand that what is the importance of the component of the forces, because all the forces not become peak at the same time. Okay. Now, with this let us finish here. Now, you can see this equation again I am coming. Now, here we now discuss all these components, right. We discuss the J Morse, K, M, A, B, C, X, now exciting force also, and then this exciting force I now divide into different component, okay, which is the force coming because of this wave, which is called the Froude-Krylov force. This we just discussed. Once we get the phi I, integrate the phi I, get this force, but we not yet discussed the other three thing, which is this A, B, C. C we discussed, but we did not discuss the another component, which is basically the A. So, now discussion of the A and discussion of the B is not yet done. However, discussion of the FD also is not complete, only we discuss about this Froude-Krylov forces. So, in our coming lectures, we are going to discuss this, how we can obtain this A, how we can obtain this B, and how we can obtain the diffraction force, which is FT. Okay. Till this point, thank you.